Hi, today we start exploring direct methods for the solution of systems of linear equations. Now, here we have a map. We will start with the simple case of system with trivial solution, and by that we mean systems where the matrix is either diagonal, lower triangular, or upper triangular. After that, and for the general case of a linear system AX equal B, where matrix A is neither diagonal nor triangular, we will discuss two types of methods. Elimination methods, where we will basically review the classical Gauss method we already know from linear algebra, and then factorization, also called decomposition methods, which are based in expressing matrix A as the product of two triangular matrices. Here we will discuss Kraut method and its symmetric counterpart, the so-called Cholesky method. Let us start with the simplest case of a system with a diagonal matrix, that is, a matrix where all off-diagonal entries are 0. This is in fact n uncoupled scalar equations. Indeed, the first equation reads d11 x1 equal b1. The second equation is d22 x2 equal b2, and so on. For this reason, the algorithm consists simply in performing n divisions, shown here. And of course, we need all diagonal entries dii to be non-zero to avoid division by 0. In other words, we need matrix T to be regular, to be inversible. The operation count for this algorithm is n operations, more specifically n divisions. It is also rather simple to solve a system with a lower triangular matrix L with 0 entries in the upper triangle. These systems may be solved starting from the first equation and going down. Indeed, the first equation involves only a known x1, which can be computed by performing a division. Second equation reads L21 x1 plus L22 x2 equal b2. And because we have just computed x1, x2 can be obtained simply as b2 minus L21 x1 over L22, and so on. Okay. So we may compute the xi sequentially, starting from the first one and down to the last one. In other words, the forward substitution algorithm starts by computing x1 and then sequentially for I, 2, 3 dots n, the rest of the unknowns. Okay. We again need for all diagonal entries Lii to be non-zero to avoid a division by 0 here. In other words, we need the triangular matrix to be regular. And an operation count, taking into account all the sums, products, and divisions, reveals that solving a lower triangular system requires n squared operations. Situation is very similar with an upper triangular matrix, that is a matrix U with zeros in the lower triangle. The only difference now is that we start from the last equation and move backward up to the first one. Indeed, from the last equation we may obtain xn by performing just one division, and we then compute the remaining xi sequentially. That is, the so-called backward substitution, or backsubs for short, algorithm consists simply in computing first xn and then xn minus 1, x minus 2 dots x1 sequentially. Again, we need all diagonal entries in U to be non-zero, to avoid division by zero. Matrix U should be regular. And not surprisingly, the operation count is exactly the same as for a lower triangular matrix. That is, we need to perform n-squared operations.